I use this Marantz amplifier as my main hi-fi amplifier. It spends most of its time amplifying the sound from the TV as well. But I've noticed that it does run very warm. When it's been on for a while, the top gets quite hot, even when it's not doing anything, when it's just sitting silent. And I measured the power consumption. When you first switch it on, it's about 23, 24 watts. When it's just been running for about 10 or 15 minutes, it's up to 65 watts, and that's doing absolutely nothing. So I'm a bit concerned about that, especially with the current energy cost situation. I'm going to have a look at it and see if I can work out what's going on. So with the lid off inside, it's got features which you find in most hi-fi amplifiers. There's a standby power supply circuit here, which switches the main power supply, this great big toroidal transformer. You've got some pretty chunky heat sinks for the main power output. Two nice big beefy capacitors down there. What I assume is the preamp board underneath, and then this section here, it's a network amplifier, this one, so it's got built-in internet radio and Spotify and Apple Music and all that sort of thing. So you've got that section in that shielded box there. But what I'm interested in is the idling current, because these heat sinks do run pretty warm even when they're doing nothing at all. And I've found a download of a manual. It's a bit dodgy to see, but I believe these are the adjustments here for the idling current for the left and right channels, and the measuring points are these connectors here. So I know what the adjustment should be, and I'm going to try and connect a meter now and see if I can verify whether the idling current, the bias current for those transistors, is too high, or if it's about right, and maybe this power consumption is what I would just have to live with. So the first thing you're supposed to check is that there's no DC offset on the speaker terminals, and that's adjusted with two pots on the main preamp board. It's difficult to see, but I'm shining the torch at one there, so that's one of them, and the other one is just down there. The camera probably won't focus on those because it'll focus on the things above. And at the moment, we've been switched on for a while. I'm getting 16.3 millivolts or so on the left channel and 11 millivolts on the right, and that's just measuring straight across the speaker terminals with the volume turned right down. And it's supposed to be obviously 0 volts plus or minus 20 millivolts. So they're both settling on the slightly high side of that. I may just do a little tweak now off camera, because it's going to be very difficult to hold the adjuster and the camera at the same time, just to see if I can get those closer to 0 before I have a look at the idling current adjustment. Well, that is a remarkably sensitive adjustment. I have got a little bit closer to 0, so we've got 2 millivolts on the left channel jumping up and down, and it's on the right channel, it's sort of jumping between about -1 and +1 millivolt. I think that's as close as I'm going to get. Obviously, as thermal conditions around the amplifier change, that's going to drift. But the spec is 0 plus or minus 20 millivolts, so I think we're well clear there. So I'm now connected onto one of these test points. I don't have an appropriate connector, unfortunately, so I've had to fashion a connector out of these Molex pins, using the cord grip end pinched up to try and get onto the pins. I'm very keen to avoid a short circuit here. A bit confusingly, these connectors have a middle pin as well, but shining a torch through the PCB, it doesn't look like the middle pin is connected to anything. So I'm across one of the test points. I've got my meter here on millivolts, but because I'm a little bit nervous, I don't want to short anything and damage any of the power output transistors, I've actually plugged into my light bulb limiter, so the current to the amplifier is actually going through at the moment through that 150 watt bulb, and I'm about to switch on. It'll probably come on and then dim down, so we'll just see what happens. There you go, I've turned it on. That's now drawing current through the bulb, and I've just heard the relay click, which means it's applied the final power. The protect relay's clicked in. Voltage across the amplifier, 228 volts, 26 watts, so we'll just wait for that to warm up and it'll get up to its 50 or so watts. And as nothing seems to have shorted out, I'm going to now bypass the light bulbs with that switch, so they're now getting full power, which is what I need really to make this adjustment. Well, now this is interesting. The amplifier's been on for about 10 minutes and I am measuring 42 millivolts across that test point. Now that test point is basically measuring across a resistor that's in series with the bias current going to the output transistors. That's my understanding of it. So the reading that you get in millivolts here is proportional to the amount of bias current that has been set for those transistors. And the manual says it should be 17 millivolts. So that is way higher than it should be, and that would definitely explain why this is running hot. And also, if I look at my power consumption, 63 watts, that is a lot of power given that this amplifier is sitting here doing very little other than running the preamp, the RF board. So that degree of overbias is bad for the output transistors. They're going to be stressed running hot. The extra heat in the amplifier is not going to be good for capacitors, and overall it's not good for my electricity bill because this sits here in the evening amplifying the television for long periods of time. Running at 65 watts when it's hardly doing anything is really not good. So I'm going to let this cook for a little bit longer. You see we're still rising. I'll let it stabilize to the point where it stops increasing, and then I'm going to try and adjust that down to the 17 millivolts that it specifies in the manual using this pot here. Now that's just one channel. This is just, I think, the left channel, or it might be the right. I'm not too sure which way around they are. I've got to do the same on the other side. But let me leave it for a little bit longer to warm up, and I'll come back and see if I can adjust it down. Right, so we're back at the amplifier. Everything seems to have stabilised now. It's dropped by a couple of millivolts, but we're still way too high. So the adjustment instructions say, first of all, set for 10 milliamps, so 10 millivolts, wait 5 minutes, and then adjust up to 17. So I'm going to try that now on this channel. I imagine it's going to be a very sensitive adjustment. Okay, yeah, it is. So we're going to come down to 10. It is very tricky. It's a shame they didn't put multi-turn pots on here. So I'm going to come down to 10. Nearly there. Okay, that's close enough. And then I'm going to wait 5 minutes and adjust it up to 17. And just out of interest, let's have a look at my power consumption now that we're down at 10. So we were at about 62, 63 watts, and we're down to 48 now. So just adjusting one channel, we've saved about 14 watts of wasted power. So 5 minutes has elapsed. We've still got 9.5 millivolts at that test point. Dropped a little bit. The manual now says adjust up to 17 millivolts, and that is the final adjustment, because apparently when the lid is on and the temperature increases even more, it will drop to its optimum operating point of 14 millivolts, which equates, according to the manual, to 70 milliamps of bias current. Now this is already pretty hot, so I'm not too sure how much more it will drop, but I'll follow the manual anyway, and I might do an experiment at the end by actually putting the lid on and measuring. I can probably get the wires just under the lid just to see if it does drop after half an hour. But anyway, so I'm going to go back up to their 17 milliamps that they suggest. We're nearly there. Sorry, 17 millivolts I meant. Okay, that's good enough. I'm going to leave it there, and I'm now going to reconfigure and connect to the other channel. So I've reconfigured the setup. We're now looking at the test point on the other channel. The amplifier is still warming up. It was only off for a short time, but the reading is still changing. And this channel is even worse. We've got 50 millivolts across this test point that's only supposed to have 17 or 14 when it's warmed up. So this is not right. This is definitely a misadjustment. This was as the amplifier came from the factory a year ago, and it's been burning off power unnecessarily due to this misset bias. Again, I'll come back in a few minutes and adjust this. I'm also, when I finish these adjustments, I'm going to recheck the DC offset, make sure that hasn't changed, and then I will run the amplifier into a dummy load and have a look on the my PC scope just to see if there's any crossover distortion. So that would be a problem if the bias current was too low. We would have crossover distortion between the top and bottom half of the sine wave at low input levels. But we'll try that and hopefully there won't be any. Let's see what happens. Gosh, we're still climbing 52 millivolts now across that test point. Right, we seem to have topped out at about 52, 53 millivolts on this test point. Interestingly, I've noticed my mains voltage. I think when I started this I was reading about 242, we're now down to 238, so that has a bearing on things as well. But I'm going to adjust this down now to the initial 10 millivolts and then, as per the manual, leave 10 minutes and bring it back up to 17 millivolts. So let's see if we can adjust this. I mean, that is a shocking amount of overbias, really driving those transistors hard and wasting a lot of power. It's either been very misset at the factory, or do they overbias them because it sounds sweeter? I don't know, but we're going to bring it down. So we're getting close to the 10 millivolts that they want. And then I shall stop again 10 minutes later. I'll come back and bring it up to 17. And as I say, the theory that they say in the manual is from 17 it will drop to 14 with the heat built up once the lid's on. Okay, I'm going to stop there. I'll come back in a moment. Okay, we're back. I'm at 9.2 millivolts. So I'm going to, as per the manual, nudge up to 17. And the theory being that when it's got the lid on, that will drop to the optimum 14 millivolts, which the manual says equates to 70 milliamps of bias current. As I say, I think it may be a little bit high still because the amplifier is pretty warm. Okay, there we go, 17. Oops, tad high. Okay, I'm happy with that. And let's just have a look and see at the power consumption now. Yep, 36 watts. So with both channels set to what the manual says, I brought my power consumption down from about 62, 63 watts to 36 watts. That is not insignificant, and that's a lot less power consumption for my electricity meter, but also it's a lot less heat just being wasted and potentially stressing and damaging the amplifier. Right, I'm now running the amplifier, having made the adjustments, with the lid on, a bit precariously because I've had to poke the test wires out. The idea in the manual was that these readings, as the temperature builds up inside, will drop to close to 14 milliamps. Because the amp was pretty warm from being overbiased when I was adjusting it, it may not drop that much. I'll be interested to see, so I'm going to leave it half an hour and we'll see what happens. But at the moment I'm very happy because looking again at my power meter, 34 watts, 34.5 watts, and we started off somewhere between sort of 62 and 65 watts, which is very high. So about half an hour has now elapsed with the lid on, and we've ended up with 12.9 millivolts across the test point on the right hand meter, which is actually the left hand channel, confusingly. So that one has gone down as they expected in the manual. It's slightly overshot. It should be at 14 millivolts. Interestingly, the other channel, which is the left hand meter but the right hand channel, has actually nudged up a little bit to 18.6 millivolts. Not quite sure why that one's tending upwards. That's probably not a great sign. But what I'm going to do, I'm going to adjust them quickly now while the amplifier is up to temperature, to as close as I can get to 14 milliamps. But you are on shifting sands here because the mains voltage is varying all the time. So at the moment I've got 238 volts across this amplifier. If I drop that by switching in these two light bulbs in series with the amplifier, so that's a 210 watt bulb with them both on, so they will become in series with the amplifier as soon as I turn off the full power switch here. So I'll go back to the meters, and I'm now going to introduce the light bulbs in series. Here we go, and you can see the voltages have gone up a little bit, so the bias current has actually adjusted itself up, and I've now got 231 volts across the amplifier. So dropping the voltage across the amplifier by 7 volts has changed that. If I now switch out the 60 watt bulb, so we'll probably get about 220 volts across the amplifier, then they go up even more. So you are on shifting sands. The mains voltage is going to be varying all the time, but I'll go back to my full power, and I'll adjust for 14 millivolts on both of them, and I'll call it a day. I'm also going to quickly check the DC offset as well before I do that. Bear with me. So I'm just going to use the 1 meter for this. I'm going to connect it across the left-hand channel, and the DC offset is virtually 0. Remember, you've got plus or minus 20 millivolts allowance here, so that hasn't changed with any of the adjustments we've made. And I'll just check the other channel. Yeah, minus 1.4 millivolts, absolutely fine. I'm not going to make any further adjustment to the DC offset settings, but I am going to adjust the current at those test points down to 14 milliamps as quickly as I can, while the amplifier is still at optimum temperature. And then after that, I need to check that we haven't affected its audio performance. And this is where we've ended up with the bias adjustment, 14.4 and 14.7 millivolts at those test points, but it really does vary enormously with the input voltage affects it. We're back up at 240 now, but even just taking the lid off, I don't know if I can easily do one-handed, but if I remove the lid and let the heatsink exposed to the wider air, and you'll now see those two readings are immediately, well, one of them certainly changing, and in time the other one will as well. It's quite surprising how finicky they are, really. So this is the setup for my amplifier testing. I've got the amplifier outputs connected to this switch box, which I use to switch between my amplifier and speakers under the desk, which are normally for the PC, and devices on top of the desk. So I've got the amplifier connected to that, switched through not to the speakers but to these 8 ohm dummy loads here. I'm using the picoscope device to monitor that output. The switch box has some monitor points on there. And also this picoscope has the ability to generate sine waves, so I'm using the sine wave generator function on that to feed one of the inputs, the CD input on the amplifier. And then that is connected to the PC here, and I'll go to OBS in a minute and try and capture what I'm seeing. So my aim with this is to run a very small signal into the amplifier, which I think will show up any crossover distortion most easily, and then we'll just generally check that it seems to be behaving normally again. So this is my first attempt to check to see if I've introduced any crossover distortion in the amplifier by lowering the bias setting. I'm using a signal source which is built into the picoscope. I've got it set to a very low level, which is where you see crossover distortion most, and these traces are across the output of the amplifier taken at the speaker terminals, which are running into an 8 ohm dummy load, and I've got the amplifier turned up. And straight away you can see there's some horrendous crossover distortion here, this little knee in the transition from the lower to the upper half of the sine wave. Now my first reaction on seeing that was to take the lid back off the amplifier and turn up the bias control on one of the channels back to its original 40 millivolt setting, but that made absolutely no difference at all. So my next thought was, well, is this signal generator a problem? And you'll see what happens next when I try and run the output of that straight back into the picoscope inputs. Right, I've now got the picoscope signal generator connected straight back to its own inputs, and yeah, we've got the crossover distortion. So this signal generator at low levels is pretty much useless. If I increase the amplitude, I'll just change the scale here, and I increase the amplitude of the signal, it is clean. So it's clean at high levels, but it's useless at low levels, and you need low levels in order to be able to check crossover distortion on the amplifier. So I'm now going to try and find an alternative tone source to test my amplifier with. Right, after a lot of faffing around, I've managed to get a tone source coming from a laptop which looks reasonably clean. That's the red trace here, and it's very low level, that's why it's jittering around. The picoscope's not very good at locking to it. That's 20 millivolts RMS on the red trace, and the green trace is one output from the amplifier, left or the right channel, I can't remember which. I'm now going to turn up the gain on the amplifier, and we'll just see if it looks clean on the output. So I'm increasing now, I'm a little bit away from the microphone, so coming up now with that very small signal going in, and so far that's looking great. I'm not seeing anything at the crossover point. That's looking fine. I'll take it up. So that's the amplifier up almost as high as it'll go with that very tiny signal going into it. I'm now just going to try and reduce the signal a bit more. I'm just going to have to come away from the microphone to do that. So I'm going to reduce the input a bit more. Obviously as it gets lower the trace will get noisier, but even at that low level I'm still not seeing any crossover distortion on the amplifier output, and that's now 7 millivolts going in. So that is pretty good. I'm happy with that. And just for completeness, I'm going to check the other channel, so bear with me one moment. Okay, this is the same setup as before, but now I'm looking at the other channel. So with a small signal going in, it's 18 millivolts, and that's the output on the green trace, and again I'm not seeing any crossover distortion. I'll just take the input level, the red trace, down a little bit again. Yeah, I think it's fine. I don't think there's any problem. So reducing the bias current through the transistors on the amplifier has not affected the performance in terms of crossover distortion, but it has radically reduced the idling power, almost by half. So I'm very happy with that. So this was really just going to be a show and tell video about the problem I found with my amplifier, but I probably ought to try and explain what the adjustment was that I was making. Now, I'm not an amplifier expert by any means. My understanding of these things is quite rudimentary, but I'll attempt to explain it as I understand it. So this is a circuit diagram of the left channel of my amplifier, and the speaker outputs are here, so left speaker out and ground. And if you follow that brown dotted line, it meets these two 0.1 ohm resistors which sit in between an NPN and a PNP transistor. Now these are the transistors, the big ones, bolted onto those heat sinks, and this amplifier is working in what's called class AB mode. So this transistor is dealing with the positive going part of the waveform, and this one is dealing with the negative going part. But the problem with using transistors like this is you have to turn them on a little bit. You have to set the DC conditions such that current is always flowing through here, just enough so that when you apply a signal here, the transistor doesn't have to go through its 0.6 volt drop before it starts turning on. So you need current continually flowing from the positive rail here through this NPN transistor, through these 0.1 ohm resistors, which are almost as if they're not there because that's such a low value, through this PNP transistor, and then down to the negative rail. Now what I was doing, I was measuring across this test point here, which is actually across these two 0.1 ohm resistors. Now these are very low values, so they don't really interfere with the operation of the amplifier, but what they do, they provide a voltage drop so that you can measure a voltage here that's proportional to the current through these resistors. And by choosing a sensible value like 0.1 of an ohm, so we've got a total of 0.2 of an ohm here, that means you can quickly translate the voltage you read here to the current through here. So for example, if you read 10 millivolts here, because you're reading that across 0.2 of an ohm, you've actually got 50 milliamps flowing through here, so you've got 5 times the current through here that you read in millivolts here. So I was setting this ultimately according to the manual for 14 millivolts, which equates to 5 times 14 or 70 milliamps through the transistors, which is what they wanted. And the adjustment I was making was this potentiometer here back in the driver stage. So this is where the DC conditions are set up, and this adjustment affects the bias on these two transistors, and then ultimately that means it affects the total current flowing from collector to emitter through both of them. Now clearly, if you turn this up too much, if you turn these transistors on too hard, they're just going to waste heat doing nothing, and that's exactly what was happening when I found the amplifier. It's not only going to waste heat, it's going to stress the transistors and generate unnecessary heat inside the amplifier, which is going to stress components that are prone to temperature issues like capacitors. So the amplifier is now back in its normal place. It seems to be working fine. I've left it running through the power meter though, just to show you something. At the moment it's in standby, and we've got a power consumption of half a watt. So that's within the requirement to have a standby consumption of less than a watt. But let me just make an adjustment to one of the settings in the menu, and I'll show you what a difference that has on the standby power. Right, I've made an adjustment to the menu settings for this amplifier. It's back in standby, but this time we've got a power consumption of 4.8, 4.9 watts. Now that's a continuous 24-hour draw, and all I've done is turn on the setting in the menu that enables control from the network. So basically the amp is waiting to be switched on from the app on the phone. Now I think this is a bit of a cheat, because yes, the amplifier does meet its half watt or less than 1 watt standby power consumption, but to use features that you might expect to be available all the time, you have to have a standby power which is much higher. That's not insignificant, running 24 hours a day. And I think it's a problem with other smart devices as well. I've got some Yamaha Bluetooth and wireless speakers, and they have exactly the same issue.